We first have to find the area between two curves. It's easy to identify that the straight line is the lower curve, the x minus 2. The upper line is the ln of x, therefore. And we'll also need to find the points of intersection. So let's call the beginning point of intersection B. And numerically we see that that is 0.15819, and that the end point we'll call E, and it's 3.14619. Again, we find these by putting each equation separately into our calculator and then solving for the 2 points of intersection. So part A just asks us, as I said, to find the area between the curves. We'll go from the beginning to the end. The upper function minus the lower function. And when we evaluate numerically, we get 1.94909. B asks us to revolve. Now, the point that we're revolving about is, this is not to scale, but it's down here below the intersection point of the area that we're going to be rotating. And so because this lower bound of the area is not in direct contact with the axis about which we're rotating, we know that means what I would call a carve out problem. Most books call this a washer problem, but for reasons I've explained elsewhere, think that's a poor way to think of the problems. At any rate, what that means is that we're basically going to take this upper curve, rotate it about this point, and so we're going to create discs that look like this sort of thing. Obviously that's not the best work I could do, but then we'll subtract off from it this straight line rotated about that same axis, and that will create another set of discs that will look like that. And it's the difference between these, the solid volume minus what's being carved out, that gives us our answer. Again, that's going to take the shape of pi times the radius squared from beginning to end for the first one, and then the second one we'll carve out. Again, pi from beginning to end, some radius squared dx. Again, with the washer method, they put both of these integrands inside the same integral. I think that often leads to mistakes, so we're not going to do it that way. So all that's left is to understand what the radius is. In this case, the radius extends from the top curve, ln x, all the way down to the axis. Now the axis is at y equals -3. It's just easiest to think of this as another curve. And so the radius is ln x minus -3. It's going to be the same as ln x plus 3. This carve out is from this curve down to the y equals -3 line. And so that's x minus 2 minus -3. The two amounts we get when we evaluate these numerically, this comes out to 107.21079, and this one, on the other hand, comes out to 73.01218. The difference between them equals 34.19861. Part C asks us to set up an integral but not to have to evaluate it. And in this case, we're rotating in a different way. We're going to revolve our area around the y-axis. So that's going to give us these sorts of disks when we do our volumes of revolution. Also, because the line closest to the y-axis, which of course in this case is the axis of revolution, is not in direct contact, this problem also has to be treated as a carve-out problem. In this case, however, we're going to have to work with respect to the variable y, integrating with respect to dy. And so we have to rewrite the radius functions as functions in terms of y rather than in terms of x. So the first function, we had y equals x minus 2. That transforms into the function x equals y plus 2. The second function, ln x, previously equaled y. Now we're going to rewrite that as x equals e to the y, just based on our knowledge that the inverse of the logarithm function is e to the variable in question. What happens to our limits of integration? Well, we're using the y limits of integration instead of the x limits. And we can see that the y limits are always 2 less than the x limits, just based on the relationship from the one line. Fortunately, we don't have to solve for anything more complicated than that in transforming from the x beginning and end points to the y beginning and end points. And so we finally take an integral that looks like this. We'll go from the beginning point minus 2 to the end point minus 2. It's an integral dy. We'll use the carve-out notation, so we're going to treat it as two separate integrals. And it still is a disk or washer method, so it's still a pi r squared issue. And what goes into the first one? It's the top curve, but in this case, because we're looking at it sideways, it's just the curve that's farther from the axis of revolution. That's going to be y plus 2. And minus nothing, because it would really be technically minus 0, because it's minus the x equals 0 line. And then the other curve is going to be e to the y, again minus 0, if you will. And that's the total setup of the integral. That's all that this problem asks for, so we're done.